Hey there, welcome back to another lecture for Calculus 1 in spring 2020. I want to talk with you today about packet number 25. We're going to be talking about section 4.2 in our textbook, extreme values. This is the start of several sections, non-consecutively necessarily, on optimization, which is the realm of finding optima of functions. So our main outcome for this lesson is going to be an algorithm for how to find the absolute min or max of a function over a closed interval. I have 3 additional YouTube videos about this content that I would invite you to check out if you'd like additional perspective on this. And I would also like to say that this is not the only stuff that we're going to do. I want you to watch out also for the terminology local min, max along the way, which we're going to reuse again later, absolutely. So the first thing that we need to do when we set up I'm talking about optimizations, is talk about optima. And so we're going to talk about absolute optima first. That's the first definition I'm going to give you, and then we'll do a couple of pictures to demonstrate it. So one thing that I want to note is that what we're going to be doing here is we're going to be finding the minimum or maximum values, and those are optima, not optimal, optima, the optima. It's plural for optimum, and minimum and maximum. Okay. So let's do a little setup. Let's let f be a function on an interval I, and let's let a live inside of I. So we're considering a point inside of an interval over which the function is defined. We're going to call f of a, the function value f of a, we're going to call it the absolute maximum over I if f of a is bigger than all other f of x's for every single x inside of the entire interval I. Because you can't find anything bigger than it. Note the inequality right there allows equality. It's not strict. So it's possible that this value is achieved multiple times. Similarly, f has an absolute minimum on an interval I if f of a is always smaller than every single other function value for every single point inside of the interval that we're considering. So let's draw a couple of pictures. Actually, I think I should stress this note here. If I just say maximum without qualification, I mean absolute maximum. So if we don't specify what kind of max, then we mean absolute. And same for minimum too. So and that's because there's also the concept of local min or local max. And we need to be able to disambiguate. So if I don't specify, then the assumption is that we're talking about absolute. If I don't happen to specify the interval I'm interested in, then we mean for the interval to be the entire domain of the function. So let's move down a little bit and talk about the concept by drawing a picture. So I want to draw a couple of things on this. I think first thing I'd like to do is draw a function and specify an interval. So let's go ahead and draw a function. There's a function, and let's specify an interval. How about I do that in red? Let's consider that to be my interval. It's my scripty I. Let's call its left endpoint A and its right endpoint B. For this function, the way that I've drawn it, if I try to find the minimum value appears right there. So let's label that. Let me do with, say, green. So this value right here, that's that height right there is going to be, let's call this little m, f of m. And if we try to find the maximum value, it's going to occur right there, just to the, I'm going to highlight that with a smaller thing, right there. And it looks like we're just to the right, the way that I've drawn it, just to the right of the interval. So that's f of, let's call that capital M. These are the global maximum and minimum of this function over this interval. Let's draw another function. Let's say choose a nice bold color here. Let's say do light. Can we do light purple? And I want to draw a function that's kind of like curvy up. Maybe kind of it's similar to like the log function. So let's call this function g, shall we? And I want to consider the minimum and maximum values for g over the interval I. So we're going to think about the same interval. They occur at the left and right, min and max. And so I'd like to highlight that fact right there and right there, this super important fact that the min or max can occur at the boundary. And so it's really important to pay attention to that fact as we do this process. Let's turn the page. So I want to define the concept of the critical point. Critical points are numbers inside the domain of the function. So the function's defined there. And it has one of two properties. Either the derivative is 0 or the derivative does not exist. Either of those two conditions will hold for a critical point. It's not possible for both of those things to be true because if it doesn't exist, it can't possibly be 0. And if it's 0, it most certainly exists. So let's draw a couple of examples of functions with these properties. So let's just kind of draw like a little like wavy dealy like that. Let's label the critical points of this function. Critical points are where the derivative is 0. Right? At all of those places, it's true that f prime equals 0. Things can happen in a couple of other ways as well. So I want to start by drawing a function that does that. And then let's give it a corner and let's give it a cusp like that. Corner, cusp, and there's this particular point right here where the derivative f prime is 0 also. But it doesn't happen to be a min or a max like all the ones on the left-hand side were. Right at the corner and the cusp, it's true that f prime does not exist at those values. It's not well defined because there's no unique tangent line, right? I can't be like there's no tangent line that fits this thing. It could be anything. There are left and right derivatives for it, but there's no derivative for it. So that's the definition of a critical point. I think based on these two pictures, I want you to note some particular things that if we're not talking about endpoints, then one thing you should pay attention to from these diagrams is that optima seem to occur critical points. And they do, as long as we're not talking about boundary ones. Okay? Let's turn the page. So I want to talk about local optima now. Local min and local max are when the function is a minimum or maximum over some interval that contains that particular point. I think the best way to do this is via picture. So let's draw a picture of a curve on the left-hand side, and I'm going to do it like that. And let's consider an interval, say from there to there. So that's my interval. My local optima are all of those places. And they can occur at boundary points too. They can also occur if I have a function that looks like that. They can also occur in the middle of the function as well. One thing that I also want you to note is that the global min or max is also a local minimum or maximum. In this section, we are not focusing on how to determine all of these things. So in the section that we're working on right now, we're going to do an algorithm for finding the absolute min or max. And when we come to the next section, 2.5, we're going to talk about how to find all of these. So an algorithm for dealing with these is upcoming. I say we have to discuss local optima now, even though we're going to find global optima in this section's algorithm, because discussing critical points forces it. We'll find local optima in the next section, section 4.3. So a local min or a local max is a min or a max over some interval. So in particular, what I'd like you to note, I'd like to focus on this point right here. So let's focus on this one right here. That is a local min, and there's a smaller one. This one's more minimum than the point that we're talking about. Let's go ahead and label this. Let's call this star. So star is the one that we're thinking about. And so depending on the little interval that we're thinking of as containing our point that we're talking about. So I've got a point C, say, where this local min occurs, and I can find about this point some small interval that just excludes the other stuff that was bigger. So we only have to think about what's going on inside of this tiny box. So if I can draw a tiny little box around my point that I'm thinking about, and that point is a min inside of that box, then that min is a local min. If no matter how big I draw my box within my interval, if no matter how big I draw it, that one's always the min, then it's the absolute min, or what we call the global min. Let's turn the page. So we're going to find the absolute mins and maxes of a function over a closed interval. And I'd like to stress again that that language note, if we just say the min or max of f without saying the interval that I'm over, then I'm just meaning the mean or max over the entire domain of f. And I really mean the absolute, right? So if I don't say absolute, then I mean absolute. If I don't say absolute or local, if I don't disambiguate those things. So there's a theorem that supports what we're going to do here. A function over a closed interval I has a minimum and maximum value in I. It actually attains these values. Right? This is a money-back guarantee. There exists a min and a max of a function over a closed interval. And we're going to talk about how you find it. So I would like to stress the fact that this requires a closed interval because there are things that can go wrong if I allow open or half open intervals. So it's closed. That means it's not open or half open. Right? It has to be closed. So why does the interval I have to be closed? Well, let's choose an interval. Let's say, consider that to be my interval. And let's let it be open so that when I draw my function, I have to put circles there. Let's consider even the simple case of that function. I think I could have done better with those. Those weren't even on top. So that's our function f. This down here at the bottom is my interval I. Let's call it endpoint A, and let's call that endpoint B. Couple things to note here in this case. F of A does not exist, or the interval I does not include A. So both those cases kind of fall under this. In this case right here, we literally can't include A in the interval I because the function's not defined there. In this other case, in the case that we're just like leaving it out, it's just because we're leaving it out. So I'm saying, why can't we leave it out? Why are these both forbidden? Well, they're both forbidden because at the left endpoint down here, right, we can zoom in on it, but like the function doesn't actually take on this value. So if we think about a sequence of points marching toward the left, if we think about a sequence of points marching toward the left here, right, we're getting closer and closer. But we never make it. Sure, the limit exists in this case, right? But the function doesn't actually take on that value. And the same thing going this way. We're getting closer and closer, but it never gets there. So we have to fill in those dots. We have to fill in those dots. There are other things that can go wrong too. Like, let's think about what happens again if I take, I should use round ones right there. That's what they should have been on the previous one. Here, I'm going to go back and I'm going to erase these. These are supposed to be round. I think I need to eat. Those are round because it's open, right? Those are round because it's open. I could have something like the function going off like that, even if something is happening normal over here. In this case, it's going off to infinity. And so the point here is not including the boundary, BDRY is boundary, not including the boundary allows this case where no maximum occurs. Right? In this case, we can't even, we can say the limit is infinity, but the limit, formally speaking, doesn't even exist. So we have to require that the interval that we're thinking about is closed. So let's talk about the algorithm now. How do we actually find the minimum and maximum values? I think there are 3 key steps. Our textbook says 2. The first thing I like to do is to make a table. I like making a table because it sets me up for success, right? So I'm going to draw a table. I'm going to put my x's and my f of x's or my y's in the other column. First thing I'm going to do is draw a table because this is going to be my key to success. The second thing I'm going to do, it's not number 2 because it's a sub point from making the table, is I'm going to put my endpoints. And we're going to practice this. So I'm going to put my endpoints, A and B. I'm just going to put those right there right away because that way I can't possibly forget. Right? So I'm going to include those endpoints so you don't forget. Because it's easy to just go directly to finding the critical points and then forget to do the endpoints. It's a common source of error. The second thing we're going to do inside of making the table, so the subpoint, is we're going to include the crit points. So let's call those like C sub 1, C sub 2, C sub 3. However many do you have? I don't know how many critical points your function has. These are training exercises that we're giving you, so probably not too many. Then we should evaluate the function, all those points in the table. So this is going to be f of A, f of B, f of C1, f of C, however many you have. And then finally, once I've done that, now I actually have the tool that I need to be able to check it, because now we're finding we're still finding the absolute min or max. We're not finding global, so it's sufficient to have this table here. If we were doing local, then this table would be insufficient. We need additional data. All right. So I'm going to look at this, and I'm going to scan these values for which is the min and the max. And all I have to do is look at those function values, pick out which is the min and the max, and then report. I made this in flowchart form. I'm really proud of this flowchart. I like using this flowcharting tool. If I had vertically oriented video, this probably would res correctly on your screen. I'm guessing that it's not sufficiently res for you to be able to see it, but that's okay. Maybe you printed it, and then you should have it really nice and sharp because I made sure to do it as an encapsulated PostScript file, so it should print really sharp for you. So we're going to find the absolute min and max. And I started by saying, what are we given? What are we given when we do this process? We're given a function f, an interval I, and it's important to note that if I is omitted, then I is equal to domain of f. We want to find the min and max of f over that I. The first thing that we're going to do is we're going to make a table. So that's this first blob right here, is make a table. When we make a table, the first thing I like to do is add my endpoints. Right? First thing I want to do is add my endpoints because it's easy to forget to do that. So we'll just take the x values for the endpoints of the interval I, and we'll put them in the table. Then we're going to add the critical points. How do we find the critical points? So remember that crit points are of 2 flavors, either f prime equals 0 or f prime does not exist. In both the cases, it has to do with f prime, and so we've got to deal with it. So the first step that we're going to do when we are doing the critical points is we're going to take the derivative of f. We're going to find f prime. And then I like to do this one first. I like to solve where f is undefined first of these 2 steps because it's easy to forget it also. And so we're going to compute the points where f prime is undefined. That is to say, there are a couple of ways this is going to happen. We're either going to solve where the denominator of f equals 0, or we're also going to watch out for domain boundaries. What I mean by that is that's things like square root or natural log, etc., that you're going to want to pay attention to, particularly if I didn't state what I was. And then once you're done with those, then you'll go ahead and add to the table. Similarly, we want to find the critical points where the function is nice and differentiable, but that the tangent line is horizontal. All right, these are tops and bottoms of hills, nice smooth hills. So we still have f prime. We're going to compute the points where f prime equals 0. We'll solve it, and then we'll add those to the table. So now I've got a table that has both types of critical points on it, and it's got my boundary. And so then I'm ready to go ahead and construct the next step of my table. We're going to evaluate the function for every single x value. Let's evaluate the function there. Now, after that, all I have to do is locate the minimum and maximum values. Just look at those function values and find the absolute min and max in them. It's very important to note that this does not locate relative optima, just the local. So if you want local, need additional steps. Right? This is insufficient. And finally, we found those two things. We're going to conclude. We're going to write our answer clearly. And I think it's really important that you pay attention. Did the question want the function value? Did the question want the location of the optima? Or did it want both, right? Does it want A and f of A? Does it just want A? Does it want f of A? Which of those things does it want, right? Which of those things does it want? Right? Don't just have your table. What I'm saying here is like, don't just like take your table of like x's and y's that you have and be like circle done. Like, no, like I really want you to like actually like write down the minimum value of f is 5.2 and occurs at 1.59, or better yet, instead of decimal places, depending on the type of problem that we're giving you, we're going to prefer exact values. I'm guessing that some of you have been finding problems with web work. It's not really problems with web work. It's that web work wants lots of decimal places, and the way to skirt that is to use exact answers. And so I give me exact answers if you can. I'll accept floating point numbers if you can't. Let's turn the page and do some examples. Okay, so I have 3 examples planned, and then we'll call it for the day. So let's find the extrema of, that's another word for optima, of f of x equals 2x cubed minus 15x squared plus 24x plus 7 over some interval. So we're given a couple of things, right? I'm given my interval, I'm given my f, and they're saying do the extrema. That means they want both. That means they want both min and max. And I think we should also report where they occur by default. I think we should report values and locations by default, because you computed both, probably, in order to do this. So let's start by drawing a table. This is the thing that I want to use. I'm going to put my x's in my f of x's. I prefer f of x there as opposed to the label y, because here it tells me what I'm going to do. I've got to evaluate my function, right? X is going to go into f to produce those values. Our interval is from 0 to 6. Right, I'm just going to put those boundary points in right away. Now we need the critical points. that's going to be where f prime equals 0 or f prime is undefined. In this case, we happen to have that f is polynomial. And so f prime is always defined. So when I take f prime, we're going to do a whole bunch of like power rule with a constant product rule in these. 6x squared minus 30x plus 24. And I'm not going to write 0 equals 0 on that because that's not true, because f prime is this function. And then the critical points are where the thing is equal to 0. So it's true that f prime of c equals 0 equals 6c squared minus 30c plus 24. And I'll probably, as I do this, like screw up and start writing x's because it's such habit to just write x everywhere, right? But like, I'm going to try my hardest to be c's because this is only true at special points c. So let's go ahead and divide by 6 because I see that I have a 6, a 30, and a 24, and those are all multiples of 6. So let's divide by 6, and I'll get 0 equals c squared minus 5c plus 4. Ooh, and this factors as c minus 4, c minus 1. I knew that because I saw that this minus 5 right here is like, you know, 4 is 1 times 4. 1 plus 4 equals 5. This implies that either c equals 4 or c equals 1. Those are my critical points, 4 and 1. So we'll take and put those in our table, 4 and 1. And now we'll evaluate our function. There's no way that I'm typing in a whole bunch of stuff over and over. So I'm going to use a TI with the ands trick. So let's see here. I'm learning how to do a thing. So I think I can go like that, and then I can go like this. And now I have a TI calculator inside the screen that hopefully this works well. This is my first time doing this. So let's go to y equals, because I kind of want to like see a plot of the thing at the same time. Now, I went ahead and pre-typed this in. Let's make sure I typed it in correctly, because it's possible I didn't. I'll go ahead and type it into your calculator, pausing the video if necessary to catch up to me. 2x cubed minus 15x squared plus 24x plus 7. Great. So let's graph it. So I don't have like pinch to pan. I have tap to trace in this calculator. That seems good. We're interested in from 0 to 6, right? So I'm going to adjust my window from 0. I'm going to adjust my window from 0 to 6. Clear 6 graph. And now its height is super silly. So let's see if zoom fit does the correct thing on this calculator. Nope, zoom fit on this implementation of this TI does not do what it does on an actual TI. And so it adjusted my window again. That's fine. Whatever. We'll do 0 to 6 graph. And maybe I can do this without... Yeah, this is pretty mediocre. Okay, no problem. Let's go into trace mode and go 0, enter. That evaluates my function, right? Even though the scale is screwed up, that's fine. That evaluates my function. Well, that should have been pretty easy to start with because I'd have 0, 0, 0, and 7. So that function value then, my friends, 7, 6, enter, 43, 4, enter, minus 9, 1, enter, 18. So I think that using a TI with that I guess I didn't use the ants trick. I used graph trace mode. Or the ants trick. Both of those two things are really powerful for quickly producing those values. Now all I have to do as the last step, I produce my table. I've got my critical points. I've got my function values. And so the last thing I need to do is to find the ones that are the biggest and the smallest, the minimum and maximum. I think biggest and smallest are fraught. I've got one right there, and I've got one right there. Let's try that second one again. And let's label those according to what they are. Max and bin. Let's not call it good. Let's go ahead and report. The min is -9 and occurs at x equals 4. The max is 43 and occurs at x equals 4. No, wait. Which one of these is wrong? The most recent one is. Boop. 6. Sweet. That was pretty good. Let's do the next one. Ooh, this one is called a cusp. These are out of the textbook too, so if you want to see our author's written perspective on these, I would strongly invite you to do so. So I want to plot this function to start with. That's basically always the first thing that I want to do when I see a new function, is plot it, because I'm just such a visual person. 1 minus x minus 1, delete, to the 2/3 graph. Let's see here. We're on -1 to 2. What did I do wrong? This should always be defined. Why does this calculator seem to stop at 1? Okay, so if I put in something less than 1, oh, then it's split, isn't it? Zoom fit. Oh, I kept going zoom standard. Let's zoom out. Now, I think this calculator is wrong. So if I put in something around is around 0, then I have x minus 1 is around -1. So I'd have 1 minus 1 to the 2/3. And that value would be 1 minus 1 to the 1/3, which is 1 minus 1, which is 0. Yeah, so if I go trace and I go 0, enter, it's telling me that, what did I do wrong? Did I enter this thing correctly? 1 minus. I think this calculator is wrong. I think this calculator is wrong. Let's try a different calculator. One minus x minus 1 to the 2/3 graph. There. Is that so hard? Wow, I just found a bug in that other calculator. That is disturbing. Isn't that disturbing? So we're supposed to be from -1 to 2. There we go. That's about -1 to 2. Okay. I don't trust that other calculator now. Why wasn't it? Was that because the window? Oh, I know what it was. No, that wasn't a calculator bug. That was user error. Let's see, because I think y equals, no, clear, -1 to 2? Clear 2. Yeah, okay, yeah, I mean, come on. Really? The function's clearly defined there. One minus x minus 1 to the 2/3. Okay, fine. That calculator sucks. I'll use this one, even though I don't like its interface as much. Anyways, so we've got a plot of our function. Let's go ahead and replicate it. Let's draw some axes. -1 to 2. Our function, it looks like, let's trace this action. Looking at the very top right there, I don't know if it makes out, but it looks like it's at about 1, and I agree with that statement. But it's kind of hard to tell where the actual maximum is. So let's put 1 right there. And so our function goes like, function goes about like that. Okay. Okay, so let's start by building a table. X, f of x, -1, 2. Can't possibly forget those boundary points this way. The next thing we need to do is consider f prime of x, because we need to add the critical point. So let's take the derivative of, and now we're going to need the chain rule. So we're going to have a minus 2/3 x minus 1 to the minus 1/3. And then we're going to chain out a 1. Okay, fine. So looks like the chain rule is not particularly important on this problem. Good. And it might look like, okay, like, where is this undefinedness coming from? But it's really it's this minus 1/3. So if I rewrite this expression, then I would have f prime of x equals minus 2/3 times 1 over x minus 1 to the 1/3. And now we can see that the undefinedness is going to come from here. From when that's equal to 0. So we're going to find where f prime does not exist by solving x minus 1 to the 1/3 equals 0. I wanted to write that in purple. So let's cube both sides to get rid of that 1/3, right? Because 1/3 to the 3 equals 1. So now I've got x minus 1 equals 0, which implies that x equals 1. So we'll add that to our list of critical points in our table. We also need to ask where does... So we need to find f prime equals 0. That's where 0 equals minus 2/3, 1 over x minus 1 to the 1/3. And we should multiply by x minus 1 to the 1/3. And on the left-hand side here, we'll still have 0, but these ones are going to cancel. And we'll find that 0 equals minus 2/3. Okay, so that's an absurd statement, but that's okay. What that's telling us is that there are no such crit points. Right? There are no points where f prime equals 0. So going back to our table, our table now is complete. That means I need to evaluate my function at those places. Okay, they want me to give them money. Fine. That's okay. I can plug in things by myself. I don't need them. F of 1 is 1 because it'd have like 1 minus 0. F of 2 equals 1 minus 1 to the 2/3. That's 0. And f of 1. Ooh, I put 1 in the wrong place. I caught an error. Sorry. F of minus 1 equals 1 minus 1 minus 1 to the 2/3. That's at 1 minus 2 to the 2/3. That's equal to 1 minus 4 to the 1/3 power. So 1 minus, why does it keep doing that? 1 minus the cube root of 4. The cube root of 4 is in fact bigger than 1, which means that this entire value here is less than 0. So now we need to examine that table, and we'll find that the min f of x is equal to 1 minus 3 root 4, the cube root of 4, at x equals minus 1, and the max f of x is 1 at x equals 0. Nope, x equals 1. It's clearly time for dinner. So we reached conclusion on that, and we're done. So let's turn the page and go to our last one together. We've got this function. S of theta is 240 plus 24 times. Do I want to do this? We're already at about an hour. So what I'm going to do, because I feel like I would normally do this in 2 days. Would normally have at least 2 days of this optimization to kick things off, because I think it's really important to get off to a good start, because this entire chapter has stuff to do with this, and it builds up to stuff that uses this. But because the video is starting to get really long, what I'm going to do is say this is optional. You can stop here. By all means, read this in the book. And I've got lots of content online for this. The point is that I've got a graph from 0 to pi that does that, and it's infinity there, that there's a min but no max. And that's because we really have this thing because the function's not defined at the endpoints. Okay. So is there an absolute max? No, there's not. Would be infinity, but we're not allowing that really. And we should still characterize this behavior. And is there an absolute min? Then we should find it. And it's like, okay, what are we going to do? We're going to take f prime equals 0. We're going to solve for those values. And based on the graph right here, there will be one solution. And that's our min. That's our min's location. And so then we would plug in that value to f in order to get the min. That's how these boil down. Okay, thank you so much for engaging today. I really appreciate your time, and I will look forward to seeing you for our next video together. Thank you. Bye.